So our first question here is giving us a velocity versus time graph and asking us to draw a position time graph, right? So basically that's asking us, can we interpret and understand what is being shown on this graph so that we can show what that would look like the other way? So our first step is, this is a velocity versus time graph that is showing a line going upwards. In other words, what is this object doing? It's accelerating. It is going faster and faster. We are clearly showing an increase in velocity over time on this graph. On a position versus time graph, if you're going faster every second, do you go farther every second? Yeah, and not just like farther, you go farther than the second before, right? You may have only gone like 2 meters the first second, you're going to go 4 meters the second. What that ends up looking like on a position versus time graph is this. Right? Every second, so if these are all kind of equal time intervals, in this first second, I only go, let's say, this far, okay? But in the second, I go quite a bit farther because I'm going faster. And in the third second, a lot farther, okay? Every second I'm going faster than the second, or sorry, farther than the second before. Well, that we don't really know, because they don't really tell us what the starting position was. They tell us that it starts at a velocity of 2. Other than that, we don't really know where it started. We would assume probably at 0. Okay, and then for number 2, it's giving us again a velocity versus time graph and asking us to calculate the acceleration. How can I get acceleration off of a velocity versus time graph? Okay, that's one way. I could go acceleration equals change in velocity over change in time. And that'll certainly work for this question, which is also the same as the slope of the line. That's where that formula comes from, right? Y would be our final velocity, X or B would, be our initial velocity, 10, okay? And our X would be our time, 10 seconds, right? So on this one here, we've got a final velocity, or a Y, of 0, okay? Because that's where we end up, is down here at 0. Our initial being 10, and that takes 10 seconds. So we've got a slope of -1 meters per second squared, right? Or meters per second per second. Everybody all right with that? Okay, something not asked by this question that I now want you to try. Draw me what the position versus time graph of that graph would look like. I'll give you a minute or two on that one. All right, so again, not worrying about scale here, right? But our position versus time graph, do I need to go into the negatives on my position versus time graph? Because a lot of people want to do that. When they look at this graph and they see that the line is going down, they assume that their position versus time graph needs to go into the negatives. But are we ever traveling backwards according to this graph? We are doing something backwards. What is it? We're accelerating backwards, but we're not moving backwards, okay? In the entire time on this graph, our velocity is positive. We're moving forwards. We're just moving forwards at a slower and slower rate. It would be like if someone put like a bungee cord across the room, okay, and I walked into it. I'd continue to walk forward, but I'd get slower and slower and slower as the bungee cord tightened up. Everybody kind of with me there? But I'd continue to move forward. So since this graph shows the object eventually coming to a stop, we know what stopped looks like on a position time graph. It looks, how does it look? It's a straight line, straight that is horizontal, right? So eventually I need to go from moving forwards at 10 meters per second to not moving at all on a position versus time graph. That looks like that, okay? The line is steep down here where I'm going the fastest, and it's getting shallower and shallower and shallower until it's finally horizontal and I'm stopped. Everybody all right with that? Okay, that's a very common type of question, okay, to get that asks, do you understand what this should look like on each kind of graph? Okay, I want you guys to try that one. I want you to find the displacement over the whole trip and the average acceleration over the whole trip. Okay, using that graph. We'll give you a minute or two there. Okay, so for part A, what are we doing here? What do we need to do to get the total displacement? What should I draw here? Austin? Right, average velocity times time, the area underneath the line. Okay, we've got to figure out what that is. For the first section of this graph, that's relatively easy because we're looking at just a rectangle. Right, so we can just kind of go down like this and go, okay, so my rectangle's 4 long, okay, and then I've also got a little triangle here, okay, and another rectangle there that I can use because obviously during this part, my velocity is changing, so I'm going to need to use the average, which is half the height of the triangle. So our first part, okay, in here where we have a velocity of 3 meters per second for 4 seconds. So 3 times 4, we're going to go 12 meters during that part. Our triangle here is 1 second on the base, and it is 2 high. Okay, so 1 times 2 is 2, divided by 2 is 1 meter. And then we've got this rectangle here, okay, because after that it travels at a constant velocity, but I also have to include how far it would have gone underneath the triangle as well. So we go, that's 6 seconds times 1, so this is 6 meters. So we're looking at a total of 19 meters east. Okay, and that's something, guys, that people will miss. If I was to put a question like this on a test and have the graph with east there, a lot of people would miss it. Okay, always make sure you look on the graph for a vector. Oh, sorry, that's in minutes. Let's pretend that was in seconds because that's just dumb. How many people converted it to minutes? Or converted it back to seconds? Okay, if you did, good job for you. And that was extra work, right? But yeah, the units were in minutes, so we should actually convert this to, so this would be 240, and yeah, it's a bother. We'll just pretend it was seconds all along. Okay, if I want to find the acceleration, how many people have got the acceleration already? All right, I'm going to give you a couple minutes on that. Make the units seconds here because that's just going to make more sense. Okay. Not that I don't believe you could multiply by 60 and figure it out, but all right. Can I use y equals mx plus b to calculate acceleration off of this graph? I can only use y equals mx plus b if I have a linear relationship on the graph. Do I have that here? I don't have one single linear relationship. So what I have to do instead is just use average acceleration being final velocity minus initial velocity over time. My final velocity according to the graph is 1 meter per second. My initial velocity according to the graph was 3 meters per second, and that took 10 seconds. All right, so we're going to have negative 0.2 meters per second squared as our acceleration. All right, questions on that one? All right, we've already done a few like that, so those ones are pretty easy. We'll skip over those. All right. So for this example here, we got a bird that's flying south. Okay, they start at least flying south, and then its motion is described, okay, by this velocity versus time graph. Okay, I want you guys to answer questions A, B, and C there. And there is a bit of a trick in this question in one of the 3 parts. Okay, if you're really good at your graphical analysis, that is looking at your graph and telling what's going on, that you won't even notice that there's a trick. You'll just get it right. Okay, this kind of exposes some of our preconceptions a little bit. This kind of question. All right, so give those ones a try, and then we'll talk about them here in a minute. All right, let's look at part A first. Okay, so we're looking at whether the acceleration is positive, negative, or 0 for each section of the graph. So in part A, we're seeing a velocity change from -2 to -4. So is that a negative or positive acceleration? Negative. Yeah, it's becoming more negative. All right. And then B, what's happening there? 0. Yeah, the velocity is staying the same. It's staying at negative 4 meters per second the entire time, right? C is also showing a negative slope, so that's going to be a negative acceleration. Part D is flat, which means it's traveling at a constant speed. Part E is showing all positive acceleration, right, for the entire length of that. And then part F is showing an acceleration of 0. All right, and then can we calculate the value of the acceleration when it's not 0? Yeah, pretty straightforward. Okay, for part A, we've got that a velocity change of 2, negative 2, actually goes from negative 2 to negative 4, and that happens over 1 second. So negative 2 meters per second squared for A. And then same thing in C. Okay, it's exactly the same slope as A, because it goes from negative 4 to negative 6 in 1 second. Then for E, we go from negative 6 at time 7 seconds to positive 6 at time 10 seconds. Right, so over 3 seconds, we go from negative 6 to positive 6, so we have a change of 12 over 6, right? So we are looking at, sorry, I said 12 over 6, right? 12 over 3, okay, is going to be positive 4 meters per second squared. Okay, so change in velocity over change in time. Okay, the other ones were all 0, so we don't have to worry about them. Okay, C is the trick question here. Right? I can't remember the last time I didn't have a question like this on the unit exam for Unit 1. Okay, at what time does the bird change direction? Because the bird's flying south initially, right? Accelerating south, flying south. Okay, when does it start flying north? 8.5 seconds. This is where he actually starts going north. He starts accelerating north here at 7 seconds, but his velocity is negative until 8.5 seconds. After that, his velocity is positive. Okay, so this is the point right here where his velocity goes from being negative to being positive, and as a result, that's where he changes direction. Everybody with me on that? Okay, on a position versus time graph, that looks like this. Right? He changes direction, comes to a stop instantaneously, comes to a stop instantaneously, okay, and starts going the other way. Okay. All right, questions on that one? All right, so that's a good graphing interpretation type question. Okay, be a great like multiple choice kind of question, because I could put 7 seconds, 8.5 seconds, 10 seconds, or never. Okay, as some options on there or something like that. All right, so the answer's right there. Okay, let's have you try number 1 anyway. Okay, we'll talk about the velocity versus time graph part of it after. Okay, for right now, let's just have you do the calculations. Okay, no, sorry, let's just go through it together. All right, so we got a position versus time graph here, and in the first part, we start at position 0 and move to position 6 meters north. Are we accelerating or moving at a constant velocity during that first section of the graph? Moving at a constant velocity. Remember, we're now back to a position versus time graph. This says my position is changing by the same amount every second. So I'm moving at a constant velocity. All right, what's going on right here? Stephen, what's going on right there? Sorry, I got you guys mixed up. Yes, it's not moving. Okay, because the position is staying at 6 seconds. All right, looking here, okay, in this part here, we're moving which way now? Well, we're not accelerating, but we are moving negatively. We're traveling at a constant velocity now, backwards, right? My velocity is, or my position is changing by the same amount every second, right? If it was a curve, then I'd be accelerating backwards. Okay, and then we've got this section and this section here, both where we're moving negatively, okay, in backwards direction. But which one's faster? A or B? Which one's faster? Okay, B. Yeah, steeper, right? Steeper it is, faster it's going to go. All right. Well, let's have you guys try number 1 here. Okay, give you a couple minutes on number 1. Here. So we got a velocity versus time graph, okay, and the first part is just describe what it's doing, which is pretty straightforward. Constant velocity of 5 meters per second, okay, for the first 10 seconds or so, okay, and then it starts going backwards, okay, at negative 5 meters per second for the next 8 seconds after that, right? Calculating the total displacement is just calculating the area underneath the line, okay, so we're going to go 50 meters here because it's going to be 5 high by 10 wide. And then for this one here, we're going to have negative 5 times 8. So that's going to be negative 40 meters, which means our overall displacement is going to be 10 meters forward because that's the direction the graph gives us, right? So we always want to reflect the same direction that the graph gives us. All right, and then draw the corresponding position versus time graph. All right, so we're going to go 50 meters in the first 10 seconds. So I'm going to say, here's where 10 seconds is. I'm going to say, here's where 50 meters is, right? And I do that at a constant velocity. So first part of my graph should look like that, right? I traveled at a constant velocity for 10 seconds at 5 meters per second. Then I travel backwards at 5 meters per second for 8 seconds. So I end up, that's not to scale at all, 10 meters from where I started. Everybody okay with that? Okay, so you should be able to kind of do those kind of things in your head a little bit without having to do too much calculating. All right, questions there? All right. Okay, I want you guys to do 7 and 8 for right now. Okay, so working on 7 and 8, and then we'll go over those here before the bell goes. So for number 7 here, okay, we want to find the total displacement of the object, so average velocity times time. So we're going to have a rectangle here where the average velocity is 5 meters per second for 10 seconds. So that'll be 50 meters, positive 50 meters, or 50 meters east. Okay, and then I've got this section of the graph here where I have a changing velocity. It goes from 5 to 15, right? So we're going to take the base of that triangle, which is 5 seconds, and we're going to multiply it by the height divided by 2, because the height divided by 2 will give us the average velocity. Okay, or sorry, yeah, the average velocity there. So we've got a height of 10, okay, and a base of 5. Okay, so 50, and then we're going to go 25 on that, 25 meters. Right, so our total displacement there is going to be 75 meters east, according to that graph. Okay, questions on 7? All right, have we done a lot of these today? Is it something you're going to see again later? Probably. Okay, so if it's something that's giving you trouble, make sure you pop in, scheduled help for lunch or something like that to get some help. Hey, finish off number 8 there. We'll have a look at that here in another 3 minutes. Okay, so number 8's pretty easy, right? We don't even have any triangles. They're all rectangles. Okay, we've got this first part where they travel at a constant velocity of 4 meters per second, kilometers per second for 5 seconds. Right, so we got 4 times 5 there, so we got 20 kilometers. And then we've got 2 kilometers per second times 2. Okay, yeah, so we're going to have, okay, and then we have this part here where they're back up to 4 kilometers per second for another 3 seconds, so 12 kilometers there. So we're looking at 36 kilometers in total, 36 kilometers up. I have no idea what that thing is, but whatever it is, it's really moving, especially since it's moving upwards. That's impressive. Okay. All right, questions on any of those? Okay, so tomorrow we are going to be doing a lab, so make sure that you've got that SparkView app on your phone, okay, so that you can collect the data. Okay, should be a pretty straightforward lab, and you should get a fair amount of class time to work on it. We'll have the Chromebooks. Okay, it looks like everybody's in Google Classroom now, so we should be good to go for that.